Chapter 11, Part 3, Limits Involving Infinity. Now, hopefully you'll recall from the previous lesson where we looked at this particular example, specifically focusing on this guy right here, question D, limit as x approaches 2. We looked at the graph and we saw a vertical asymptote. The left side of the graph goes up forever, the right side of the graph went down forever. Since the left side and right side didn't agree, we simply said that the limit was D and E, does not exist. But there's a little bit more to it than just this. The fact that the left side goes up forever and the right side goes down forever, that right there implies that we have a vertical asymptote. I don't have to see the vertical asymptote on the graph to know that if the left side is going up to infinity and the right side is going down to infinity, then there must be a vertical asymptote between them to cause those two sides of the graphs to go up and down to positive and negative infinity, respectively. So what we have is a connection here. When we have a limit that does not exist, one of the options that could be happening is that we have a vertical asymptote. If we have a vertical asymptote, then the limit does not exist. If one side of the graph goes up to infinity and the other side goes down to infinity, then the limit does not exist. If the graph goes up to infinity and the graph goes down to infinity, then we have a vertical asymptote. There's connections between these three pieces of information: the positive negative infinity of the limit, of the left and right hand side of the limit, the fact that we have a vertical asymptote, the fact that the limit does not exist. So when I look at a problem like this, evaluate the limit as x approaches 0 of 1 over x. Now, of course, I'm always going to start with direct substitution, and when I do that direct substitution, I get 1 over 0. Remember, 1 over 0 is not indeterminate. 1 over 0 is an undefined answer. An undefined answer implies that the limit does not exist. But again, there can be more to it than that. 1 over x is one of our parent functions. Hopefully you already know the graph of 1 over x. We have a vertical asymptote, a horizontal asymptote, and then the graph exists in the first and third quadrant. Again, as we approach 0, what do we see? There's that vertical asymptote again. So not only analytically do we get that the limit does not exist, but we can say graphically the limit does not exist because I have a vertical asymptote. Right side and left side don't agree. But I don't even need the graph to know what's happening on the right hand and left hand side. If I focus just on an analytical representation of the limit, limit as x approaches 0 from the left, limit as x approaches 0 from the right. Again, if I plug in 0, I'm going to get 1 over 0. So let's try a table of values. What would happen if I looked at a table of values? If I plugged in numbers to the left of 0, that would be like negative 0.1, 0.01, and so on and so forth. If I plug in negative 0.1, 1 divided by negative 0.1 is going to be negative 10. If I divide by 0.01, I'm going to get negative 100. If I divide by 0.001, I'm going to get negative 1,000. Notice, as the x value gets closer and closer to 0, the y value, the magnitude of the y value, gets bigger and bigger and bigger. Of course, we're going in the negative direction, but the magnitude is still getting bigger and bigger and bigger. If I tried a really small number, 0.000001, I would get this really big number. That'd be negative 1,000,000. So as I get closer and closer to 0, what's happening to the y values? It's getting closer and closer and closer to negative infinity. So simply by plugging in numbers to the left of 0, really close to 0, I can demonstrate numerically that I'm going down to negative infinity. So now, without even looking at the graph, I can see that the graph of 1 over x is going down forever as we approach 0 from the left. And likewise, if I change everything to positive, as x approaches 0 from the right side, the y values are getting bigger and bigger and bigger, so we're approaching positive infinity on the right side. So I can start to develop an understanding of the graph simply by plugging in numbers really close to that limiting value of 0. Left side goes down forever, right side goes up forever, and again, this simply confirms that the limit does not exist. But we've also numerically confirmed that we indeed have a vertical asymptote. The fact that one side goes down forever, the other side goes up forever, implies vertical asymptote. So I can judge based on my parent function, I know there's a vertical asymptote, or based on a investigation of the left and right hand limits, I have a vertical asymptote. Anytime I see a left hand or right hand limit going up or down to positive or negative infinity, that implies a vertical asymptote. Let's look at this guy. We can start off the same way. If I plug in 0, 1 over 0 squared is still going to be 1 over 0, which implies that the limit does not exist. But again, I can do my left-hand, right-hand investigation to see what's really happening on each side of this limit. This time, if I just imagine going through the process of that table of values, if I plug in smaller and smaller values approaching 0 on the left side, on the negative side, because of that square, the magnitudes are still going to come out the same, but I'm always going to get a positive answer. So even though the magnitudes of the number are going to be exactly the same as I had with 1 over x, everything's going to stay positive all the way through. So as I approach 0, I'm not going to be approaching negative infinity because this fraction will never give me a negative number. I'm going to be approaching positive infinity. And likewise, on the right-hand side of 0, I'm going to get the same numbers that I got on the left side because everything's going to stay positive. So the question then becomes, well, here, both sides are going to the same infinity. Is it still a vertical asymptote? Well, yes, if you are approaching infinity, whether it be positive or negative infinity, you are mapping out a vertical asymptote. So we do have a vertical asymptote, but then how do I justify saying that the answer is D and E when the left and right-hand side agree? In the previous lesson, I told you if the left and right-hand side agreed, then that was your answer. So is the answer D and E? Yes, the answer is D and E. Because remember, a limit is a limit. It has to be limited to be a limit. Infinity cannot be a limit. Infinity is unlimited by its very nature. So even though we're going to in the same direction on both sides of 0, I'm going to positive infinity on both sides, the left-hand, right-hand side, the limit itself is still D and E because you can't technically say that you are limited by infinity. That just doesn't make any sense. Or feel free to just say infinity, all right? This is one of those quirky things about upper level math where we say things that we don't really mean, but as long as we all understand what we mean, then feel free to go ahead and say them. The answer to this question is D and E. There is no limit here. If I were to say the answer is infinity, that is implying to the reader that yes, of course, infinity is not actually a limit. I'm simply trying to convey to the reader that, hey, this limit does not exist. But the left and right hand do happen to agree that they're going to infinity. So feel free on these types of limits, if both left and right hand say the same infinity, feel free to say infinity with the understanding that the limit is D and E. So if you were to say the answer is D and E, you are correct. If you were to say the answer is infinity, you are correct. And you're actually saying twice as much information because not only are you saying that the limit does not exist, you're also saying that both the left and right hand agree. So in this case, either answer would be acceptable. Here we have another example where if I just go to direct substitution, plug in 2, I would get 1 over 0, which means the answer is D and E. But again, I could go further and investigate left-hand, right-hand behavior. But because I recognize what's going on, I know that, hey, this D and E is implying that I have a vertical asymptote. Vertical asymptote implies that my answer is either going to be positive or negative infinity. The only thing I need to know is it positive or is it negative? Quick and easy way to determine positive and negative is not to waste time going through that entire table of values. Just pick a number on the left side of 2. What's a number on the left side of 2? How about 1.9? If I plug in 1.9, 2 minus 1.9 is going to give me a positive answer. Therefore, I'm going to have a positive infinity. On this guy to the right side of 2 would be 2.1. 2 minus 2.1 would give me a negative answer. Therefore, negative infinity. So when I recognize that a limit is 1 over 0, that's telling me that I have a vertical asymptote. The question then becomes, is it going to positive or negative infinity? Just pick a number on the left and right side of that boundary value to determine whether it's going to be positive or negative. So to summarize, if the limit as x approaches a of f of x is either positive or negative infinity, if I apply a limit and I get an answer of either positive or negative infinity on either the left or the right-hand side of that limit, then we have a vertical asymptote at that x equals a value. Again, anytime you plug in a and you get 1 divided by 0, that's implying that you have a vertical asymptote. Then the question simply becomes, from the left and right-hand side, are you going to positive infinity or negative infinity? So if the answer is positive or negative infinity, then it's a vertical asymptote. Well, how about this? Instead of the answer being infinity, what if the x value is approaching infinity? In other words, the limit as x approaches infinity. So as x gets bigger and bigger and bigger and bigger and bigger and bigger and bigger, what's happening to the function? Again, hopefully you already know the answer because you remember that for the graph of 1 over x, as x goes to infinity, the graph gets slower and lower and lower and lower and lower, never actually crossing the x-axis. So I know as x goes to infinity, the graph levels off to 0. So I know on this case the answer is going to be 0 because based on my knowledge of the graph, I know that the height of the graph approaches 0. But I can more easily prove that using direct substitution. Just plug in infinity. 1 divided by infinity. If I take a number and divide it into infinitely many slices, how much is going to be left when I'm done? Well, if I take an apple and divide it among infinitely many people, how much apple does each person get? Essentially, because I'm dividing it so many times, it's just going to be 0 in the end. And whether I'm going to positive infinity or negative infinity, 1 divided by negative infinity is still going to be 0 because there's no such thing as a positive or negative 0. So again, remember when I'm looking at that graph, as I go to positive infinity, I'm approaching a height of 0. As I'm going to negative infinity, I'm approaching a height of 0. So notice what's happening here. When the answer was infinity, as I was approaching 0 from the right and 0 from the left, if the answer was infinity, I was describing a vertical asymptote. If I'm approaching infinity, whether to the right or to the left, then I'm describing a horizontal asymptote. So if the answer is infinity, we have a vertical asymptote. If the limit is going to infinity, then we have a horizontal asymptote. As long as that answer comes out to a finite number, then we have a horizontal asymptote. Let's look at a few more examples of limits to infinity. Remember, we can always start with direct substitution. If I look at this first one, e to the x. Again, hopefully you remember the parent function for e to the x. If you remember the parent function, sometimes that can help you evaluate these limits. Otherwise, we can go to direct substitution. If I plug in infinity, e to an infinite number, a number raised to a number is just going to be a number, and the larger this number happens to be, it's just going to get bigger and bigger and bigger and bigger. Therefore, my limit would be infinity. But remember, infinity technically isn't an answer, so I can either say infinity or d and e. It really doesn't matter. D and E would be the true answer, but infinity implies that the answer is D and E, but also tells me that I'm going up forever. Again, I can justify this graphically by simply remembering the graph of e to the x. Looks something like this. And as x goes to infinity, as the graph moves to the right, the height of the function increases forever, all the way up to positive infinity. So I can either simply evaluate by plugging in infinity and recognizing that e to the infinity is infinity, or I can think about the graph of e to the x and say as I go to the right, the graph goes up forever. So the answer is positive infinity. And in the same sense, I can evaluate negative infinity by plugging in negative infinity or by looking at the graph. Notice, based on the graph, negative infinity would mean going to the left forever. As I go to the left forever, the graph doesn't go down forever, it levels off at 0. So I know based on the graph, the limit as x approaches to negative infinity would have to be 0 because we have a horizontal asymptote at 0. But I could just as easily just plug in negative infinity. Remember that a negative exponent really implies a fraction. Negative exponent means reciprocal, so just flip it upside down and we have 1 over e to the infinity. E to the infinity, we already said before, was infinity itself, and 1 divided by infinity, as we already said, is 0. So graphically, I can show that the limit as x approaches negative infinity is 0, or analytically, I can prove that the limit is 0. So in this situation up here, I'm not saying that there's a horizontal asymptote going to infinity, I'm just saying that the limit does not exist. Versus here, the fact that the answer comes out to a finite number, I'm saying, hey, limit's going to either positive or negative infinity, the answer is a number, therefore graphically there must be a horizontal asymptote, which I already know to be true from my knowledge of the parent function. So what about this guy? What if I plug in infinity here? This is not so much my parent function, this is a combination of a couple of parent functions, so I wouldn't probably suggest approaching this graphically. I would just go straight to direct substitution. Plug in infinity, and I get a situation like this. Plug in infinity for x, I get infinity. Infinity for e to the negative x, I already demonstrated before that that comes out to 0. But here we have infinity times 0. So what's the answer? I know that anything times 0 is 0, so is the answer 0. But I also know anything times infinity is infinity, so is the answer infinity. Here we have another situation, one that we have yet to see, of an indeterminate form. Up to this point, the only types of indeterminate forms you've seen are 0 over 0 and infinity over infinity. Remember, we called those indeterminate because we had competing rules. 0 over 0, anything divided by itself is 1. 0 over 0, anything with 0 on the bottom is undefined. So was the answer 1 or was the answer undefined? We settled on indeterminate. We need to investigate further. In this case, again, we have competing rules. Anything times 0 is 0, but anything times infinity is infinity. So we need to use further investigation to determine whether this answer is 0, infinity, or something else entirely. This one is just another fancier form of an indeterminate form. So what we're going to do is we're going to use a trick that we just used in the last problem. That negative exponent, we're going to use that to help us simplify the limit. E to the negative x can be turned into e to the x on the bottom. So instead of it being x times e to the negative x, we now have x over e to the x, positive exponent. If I plug in infinity again, here we get a more friendly form of our indeterminate form, infinity over infinity, which is the same type of form that we learned about earlier in the first lesson of this chapter. But we still have a problem because I don't know how to simplify this further. When I dealt with indeterminate forms before, I would start by attempting to factor. There's nothing I can factor here. Or I would attempt some other fancier technique, simplification of fractions. There's no fractions to simplify. I had some examples involving radicals. This doesn't involve radicals. So I need a new method for simplifying indeterminate forms. And what we're going to do is we're going to go back to some old stuff. Recall when we first started looking at rational functions in your pre-calculus course, and we had a method for finding horizontal asymptotes. And that method came down to if it was a rational function, then we have an opportunity for a horizontal asymptote. And it came down to whether the function was top-heavy, bottom-heavy, or whether the degree on top and bottom were the same. If it was top-heavy, we said that there was no horizontal asymptote. We said that there was a slant asymptote instead, but my focus right now, because we're dealing with limits to infinity, is just horizontal asymptotes. The point was, top-heavy, there was no horizontal asymptote. The limit goes to infinity. If it was bottom-heavy, there was a horizontal asymptote, and we automatically said the horizontal asymptote was 0. And if the degrees were the same, then we said that the horizontal asymptote leveled out to the ratio between the top and the bottom, a and b being the leading coefficients of the top and the bottom. Now, back when we first talked about this technique, I didn't go into the background information. It has to do with limits. A top-heavy function is a function that's growing faster than the bottom. At this point, we need to recognize that not every infinity is the same type of infinity. Some infinities grow faster than other infinities. For example, the line y equals x grows at its own given rate. Y equals x squared grows much faster than y equals x. So I would say infinity compared to infinity squared is a slower rate of growth. So infinity is a smaller infinity than infinity squared. So how do I know which infinities are faster than other infinities? Well, it'd be helpful to keep this handy little chart in mind. The slowest type of growth would be no growth at all. Constant functions don't grow at all, such as y equals 3, y equals 7. They're just horizontal lines. If it's y equals a number, that's a constant function. It's not growing at all. Everyone beats constant functions. After that, the next slowest growing function are logarithmic functions. Anything of the form log base n of x is a logarithmic function. They grow very, very, very slowly. Remember that the graph of a logarithmic function looks something like this. So it's not growing very fast at all. Constant functions, again, horizontal lines. They don't grow at all. So if I have a race between a logarithmic function and a constant function, obviously the logarithmic function is going to win because it's at least growing somewhat, whereas a constant function isn't growing at all. After logarithmic functions come power functions. X squared, x to the fifth, x to the 1/2 is even a power function. Keep in mind x to the 1/2 is a square root function, so if I'm comparing a linear function, y equals x, to a square root function, y equals the square root of x, y equals x is going to beat the square root function because the square root function is growing a little bit slower than the linear function. But y equals x squared, a quadratic function, is growing faster than the linear function. The larger the index value, the faster that it's growing. After power functions, you get exponential functions. So instead of it being variable to a number, it would be a number to a variable. So if I think of y equals x as my standard power function, exponential functions are going to be approaching infinity much quicker. And then if I want to beat an exponential function, let's throw in a factorial. Remember factorials being that exclamation point, x times x minus 1 times x minus 2 times x minus 3 and so on. These grow much faster even than exponential functions. And I'll confess right here, I have no idea what the graph of a factorial function would look like. But by investigation, if I pick any random number for x, and I compare it to a related exponential function, then I can see that that factorial is going to be growing much faster. So by keeping this chart of relative rates of growth in mind, that allows me to tackle a question like this much easier. Whereas before I was just getting infinity over infinity and not knowing how to proceed from there, now I can recognize that no two infinities are necessarily the same. In this case, the infinity on top is represented by a linear function. The infinity on bottom is represented by an exponential function. Based on my knowledge of relative rates of growth, I know that exponential functions grow much faster than linear functions, which means that this is now a bottom-heavy function. And based on my older rules, bottom-heavy functions go to 0. So by combining old rules with new rules, I can now evaluate limits involving infinity over infinity indeterminate forms simply by remembering whether it's top-heavy, bottom-heavy, or the same. Now, just to make sure we understand that technique, let's just do a whole bunch in a row. Starting with an easy one, limit as x approaches infinity of x squared over ln of x. Why don't you go ahead and take a guess at this one? Hit play when you're ready. All right, now hopefully you started out this correctly by plugging in infinity, recognizing that it's infinity over infinity and therefore indeterminate. And since it's indeterminate, I have to do some further investigation. No amount of factoring or simplifying is going to help me, so I simply go to relative rates of growth. Because I'm getting infinity over infinity, I need to know which infinity is larger. The infinity on top is based on a power function. The infinity on bottom is based on a logarithm. I know that power functions are faster than logarithms, so this is a top-heavy function, which means my answer is infinity. If I were to look at the graph of this, I would see that as x goes to the right forever, the function itself is just going to grow and grow and grow forever. So my answer is infinity, or D and E, whichever one suits your fancy. Now the next one may look a little bit more complicated, but we're going to see in just a second that in fact it's just as easy as all the other ones. In this case, we have a combination of functions. On top, it's a factorial function, but that factorial function is actually the combination of a linear function and a constant function. On the bottom, I'm adding two exponential functions and then subtracting a constant function. So how does all this adding and subtracting affect my situation? I see factorial on the top, so my first inclination is to say that it's top-heavy. Am I right with that inclination, or is there something else going on here because of all the addition and subtraction? And the key thing to remember is that addition and subtraction really don't mean anything when we're talking about infinity. If I'm trying to go from 1 to 2, if I add 1 to 1 and I get 2, adding 1 just made a big difference. I'm now twice as big as what I started with. If I add 1 to 100, adding 1 to 1 is a much bigger deal than adding 1 to 100. If I have $1 in my pocket and I add 1, I've now doubled my net worth. If I have $100 in my pocket and I add 1, I really haven't added a lot. I mean, I've added $1, but compared to what I already had, it doesn't make that big of a difference. If I have $1 billion in my pocket and I add 1, I might as well not even add that 1. I'm not even going to keep track of it. It's a waste of my time and energy to even think about it. If I had $1 million, billion, trillion, quadrillion dollars in my pocket and I add 1, who cares? The point is, as my initial value gets bigger and bigger and bigger, adding and subtracting to that initial value really doesn't make much difference. If I have infinity dollars and I add one more dollar to it, it's essentially the same infinity. I haven't done anything to it. If I have infinity dollars and I add $1 billion to it, infinity is so much larger than $1 billion. I haven't really done anything to it. Adding or subtracting to infinity does not change your infinity. So what I like to do on these more complex problems like this is I think about a land I like to call infinity land. When I'm going to infinity land, anything that's being added or subtracted really doesn't make any difference. So if I look at that function, any piece that's being added or subtracted to whatever the largest piece is really insignificant. On the top, if I think about the linear function 2x compared to the constant function 1, that plus 1 really isn't changing anything compared to the linear function. 2 times infinity is infinity. Infinity plus 1 is still infinity, so I might as well not even have that plus 1 there. On the bottom, e to the 2x is infinity. If I add another infinity onto it, it's not going to change anything. It's still infinity. I might as well not even have that infinity there, and that minus 4 definitely doesn't matter. So now, by going to infinity land, crossing out anything that's being added to whatever the largest term is on the top, on the bottom, I've now reduced it to something a little bit more manageable. I have a factorial on the top. I have an exponential on the bottom. Yes, factorials are still heavier than exponentials. Therefore, our initial inclination that it was top-heavy was correct. All this addition and subtraction was simply there to distract. It really doesn't matter at all. It comes down to the top is a factorial. The fact that I'm adding one to it, it's still a factorial. All right, why don't you give these a try? Pause here, play when you're ready. All right, hopefully as we're going through them a little bit deeper, we're realizing that we can simply answer these questions by observation. The adding, subtracting, as we go to infinity, don't really matter. I have a square root over x squared. X squared is heavier than a square root. Therefore, bottom heavy, answer is 0. On the next one, I see a slightly similar problem, but this one we're going to see in just a second is going to work out a little bit differently. Of course, the 4x, the x, and the 5 don't matter as we go to infinity. I simply have the square root of x to the 6th over 2x cubed. Now keep in mind the square root of x to the 6th, that right there is x cubed. Since I have x cubed on the top and x cubed on the bottom, we actually have a situation where we have the same degree top and bottom. Remember, when we have the same degree, it's not top heavy, it's bottom heavy. We look at the leading coefficients. The leading coefficient on the top is 1, on the bottom is 2, so our answer would be 1/2. This one is going to have a horizontal asymptote leveling off at exactly 1/2. Couple more for you to try. Pause here, play when you're ready. Looking at the first one, I see exponential over exponential, but I see that the exponential on the bottom has a slightly larger degree, therefore bottom heavy, limit goes to 0. Next one, I have a linear function over a square root of x squared. Square root of x squared is x, so in this case, once again, we have the same degree top and bottom. Leading coefficients would be 1 over 1, so the limit is 1. So hopefully at this point you've got the hang of limits to infinity of rational functions. But what do we do when we have something like this? If you think you might have an idea, go ahead and pause here, play when you're ready. Yes, it is going to have something to do with a technique that we used previously involving functions that looked like this. But I'd be willing to bet that some of you may have trouble with the first step because it's just so obvious that it couldn't be right. But if you're not willing to try this one on your own, feel free to just watch me go through it. So what I'm going to do is I'm going to recognize that I have a binomial involving a radical. Remember that this would represent the first term, this would be the second term. I have a binomial. And we saw in the first part of this chapter that situations involving binomials, I'm going to use my conjugate method to simplify that binomial. So the way I'm going to start this off is I'm going to start off as I always start off, something new, something different. I'm going to plug in infinity to see what's going on here. I have infinity minus infinity, but I recognize that this infinity is bigger than this infinity. So a larger infinity minus a smaller infinity is still going to be infinity because I know a bigger number minus a smaller number is going to be positive. I'm going to have the square root of infinity minus infinity, and I'm not quite sure what to do with that. Is infinity minus infinity equal to 0, or is infinity minus infinity going to be negative infinity, or is infinity minus infinity, is this infinity going to be big enough to not have to worry about that infinity and it's still going to be positive infinity? I don't know. It's indeterminate. I got to try something else. So then I'm going to recognize that I have a square root that's part of a binomial. Keep in mind that this is the first term, this is the second term. I have a binomial, therefore I'm going to deal with my square root within my binomial by multiplying by a conjugate. Before I multiply by that conjugate, I have to recognize that this is really a rational function. It's all over 1. So by recognizing that I have a rational function over 1, this now becomes a very similar problem to what we did in the first part of chapter 11. I'm going to multiply top and bottom by the conjugate of the square root of x squared minus 8x minus x. When I multiply the top, I'm going to end up with that difference of squares, so it'll be x squared minus 8x squared minus x squared. And on the bottom, it's just 1 times all that, so I'm just left with all that. Of course, the x squareds are going to cancel out. I'm left with negative 8x. And then I reapply my limit. Now, of course, I'm still getting infinity over infinity, but now I have my more familiar form of infinity over infinity. So it comes down to, is it top heavy or bottom heavy? If it's top heavy, the answer is infinity. Bottom heavy, the answer is 0. Or if they happen to be the same degree, then I can use the ratio of the leading coefficients to get my answer. I see that the top is a linear function, and I see that the bottom is made up of the square root of x squared, which itself is a linear function, plus another linear function. So here's a situation where if I go to infinity land, this guy is going to drop off based on the x squared underneath the radical, but this guy is not going to drop off because this guy is not bigger or smaller than this guy. This guy and this guy are the same thing. The square root of x squared is x, and x plus x is 2x. And at this point I recognize that the top and bottom is in fact the same degree, and thus the leading coefficients give me my answer. -8 divided by 2, -4. If I were to ignore the fact that this x and this square root of x squared were in fact the same degree, then I might make the mistake of using leading coefficients of -8 and 1, but in fact these guys are the same degree, so I can simply combine them and reduce it down to -4. Now I really like this question because there's a completely different way I could do this problem that I think is a whole lot simpler, but a whole lot less obvious, but it still comes down to that concept of infinity land. If I go back to the original problem, and I recognize that I'm going to infinity, I can remember that since I'm going to infinity, anything that's being added or subtracted really doesn't make a difference. So if I look underneath the radical, I see x squared minus 8x, and I'm going to do something crazy. I'm going to add 16 to that x squared minus 8x. Now, of course, you might say, well, that's ridiculous. Why would I add 16 to something? I'm now making that problem no longer equivalent to what I started with. But remember what I said. We're going to infinity. Adding 16 to something that's already going to infinity doesn't really change anything at all. It's perfectly legal in this particular situation to add 16 because I have not essentially added anything to the problem. But by adding 16, notice what's happened here. This is now a perfect square. I didn't randomly add 16, I strategically added 16. Essentially, I completed the square to figure out what number I should add here. Taking the -8, cut it in half, I get -4, square the -4, I added 16. Notice I also didn't compensate for anything because, again, adding 16 didn't change anything when I'm going to infinity. But by adding 16, making this a perfect square, I can now factor that inside of the radical into x minus 4 squared. The square root of x minus 4 squared, of course, is just x minus 4, and x minus 4 minus x is just -4. Now applying the limit, I get the same answer I did before, -4, but through what I would argue would be a much simpler algebraic process, although that initial leap of faith may take a lot of initial creativity.